Good evening, everyone. Welcome to our 11th weekly discussion session for the Physics of Nanoscale Devices NPTEL course. I'm Jyotishwaran, a PhD student from the Department of Electronics and Communication Engineering, Indian Institute of Technology, Roorkee. So, the topics that we shall be looking at in this week are primarily MOSFET Electrostatics. So here we shall look at the 2D electrostatics model, and then we'll finally come around to analyzing what channel inversion means. So this is essentially an effect that was discussed for bulk MOSFETs, but this is also present in the case of uh, nanoscale devices like ballistic MOSFETs or other devices which we shall be looking at. So we shall come to the idea of channel inversion, and then we shall sum it up with a discussion of mass capacitance and form factor. So over here, we shall finally see the effects of the electrostatic effects such as DIBM. So form factor is very important in that regard. And after that, we shall have a brief discussion about mitigating these effects, these electrostatic effects in MOSFETs. And through that, we will enter a brief discussion, a very brief discussion of quantum confinement. So this week essentially sums up a good deal of what has been done in our previous weeks outside of, say, the Landauer transport model. And this kind of drives at the central theme of this course. So what we shall be seeing here is we shall see the effects, the electrostatic effects that are present in a MOSFET, and how these things make the behavior of the device deviate from our expected ideal behavior, and what can be done to reinforce said ideality. Okay, so yeah, so before I begin in earnest, a brief, digression. We have known so far that, like, in the beginning of our course, we started with a very brief look at Moore's law, where Moore's law essentially says every few years the transistor count per unit area is going to keep increasing. So this implies that we shall have smaller and smaller transistors, and more transistors implies the effective computational power we have per unit area of our processors, microchips, or whatever we are considering increases by that much. But what we shall see is that smaller transistors also imply, if designed properly, better operation and control. So now what we shall see is that the need for smaller devices, short channel devices, is not just governed by Moore's law, which is essentially an observation. Like, this is an observation based on the industrial trends. Like, this is not a scientific law per se. Now, what we will see in today's discussion especially is that these smaller transistors, these smaller devices, in addition to going along with the industry's trends, also offer us better operation capabilities and allow us to exert better control over them. So in that sense, these devices are also capable of performing their functions better, which gives us an added incentive to study these devices and come up with methods to fabricate these things. So this is the kind of uh, two-level motivation that we have. One is that, yes, we want more transistors and we want more computational power. Therefore, we will try to make the devices smaller and smaller. What we shall see today is that these smaller devices also have other benefits which give us the second level of motivation for looking at these devices. So this essentially, this week's discussion will kind of reinforce our original intent to look at nanoscale devices. So now we begin. So the direction convention for the 2D electrostatics model that we shall look at is given in the following figure. So for now, we shall not consider any drain source voltage. So VDS is equal to 0. We have a VG that is applied, and the substrate is also kept at 0 volts. So that is also grounded. So VGS is equal to VG. And this point over here, let me use here contrasting color. This point over here is y equal to 0. Okay, so the point at the insulator semiconductor interface, the oxide semiconductor interface is taken as y equal to 0. And of course, the y direction goes from here to here. And we also will make another assumption that the substrate is very large. This implies that y tends to infinity. While this may seem like an unrealistic assumption, uh, like typically, even if I assume this is say to the order of the substrate thickness is to the order of micrometers, then considering that the channel width is going to be to the order of nanometers implies that the substrate is like 1,000 times bigger. So in that sense, not substrate. In that sense, this assumption is actually pretty valid. Okay, so primarily electrostatic effects. Like essentially by electrostatic effects, what I mean is Vg determines the charge present in the channel, and this in turn determines the conductivity of the device. If enough charge is not present, the device is an off state. If the right amount of charge is present, then we have the device is on, so it's either in the linear region or in the saturation region. So linearity and saturation is determined by the value of VDS, so we don't care about that. So it will conduct if the device is on, it will not conduct if the device is off, and that is determined by the value of Vg. Like we know that there exists a threshold voltage above which the device starts conducting. So in today's, although I shall not be explicitly deriving how to arrive at the threshold voltage because I'd like to keep today's, since we are covering a lot of topics, I'd like to stay very close to the assignment problems so that it helps helps all of you who are attending this course. But nonetheless, I will give pointers as to where to look for these things. And of course, all of this has been done in the lectures, so you can always go back and look at them. So the first thing is we shall just do some derivations. So we will derive the approximate expression for the approximate electric field, the depletion charge, and depletion width of a MOSFET. So why are we looking at the depletion behavior? So the reason for that is, as discussed before, our MOSFETs essentially turn on when inversion is achieved. So what we have is the following. We have this, and I have, say, the oxide layer. So this is the and so this kind of goes further down, and then we have, so this is the equilibrium arrangement of our device. Then we have our semiconductor itself, where the Fermi level is over here, and we are considering an NMOSFET, which implies the device is the substrate is p-type, So I'm going to have the valence band over here and the conduction band slightly above over here, and this is the, where is it? This is the conduction band EC of the insulator, and this is EV of the insulator. So as we know, the, of course, let me draw the axis. What color shall I use? Green is available, now I use red. Red is more visible. So this is our energy axis, and here we have y-axis. So we are moving from the metal to the oxide to the semiconductor. So the reason why, yeah, before that, let me just finish the figure so that I can get started with the discussion. So we have AF, and then I have EC and EV. And since this is a metal, the Fermi level, the conduction level is, the conduction band or valence band levels are kind of irrelevant. What kind of metal this is, I don't care. I will just say this is the Fermi level, and everything below the Fermi level is occupied. This is an electron rich system. So we have this kind of an arrangement. Yeah, my spelling is wrong over here. So yeah, this is an MOSFET. So yes, the reason why we are considering the conventional metal oxide semiconductor layer is because it is easy to explain inversion and the related phenomena in this model. Now, if we consider a nanoscale device, then I can no longer properly define the conduction and valence band on the channel side, because those are confined systems, as we shall be looking at later. And there, these effects, like, it will be slightly difficult to intuitively understand them. So we shall use the classical model, but of course, as we move on, we will kind of generalize these effects that we are looking at here to the quantum, I shouldn't say quantum devices, to the nanoscale devices as well. Okay, so this is the system that we are considering. I shall not draw this figure again, as it will take a lot of time. But what I shall do is the following. So what we have is the this, we have the metal Fermi level, and we have the, we need not care about the oxide layer for now. What we shall simply look at is the here, let me just use a different color over here. Yeah. So yes. So at equilibrium, this is our situation. I have my, using a lot of colors is going to be a hassle. Okay, so this is the metallic side. So this is EFN, and this is the semiconductor side, EFS. Again, EFS. So as VG is applied, what will essentially happen is we are considering an NMOS. So in order to turn the device on, we would prefer to have, not we would prefer, VG has to be greater than 0. If this were a PMOS, then a negative voltage needs to be applied. So since a positive voltage is being applied, what will happen is this region, this Fermi level is going to, uh, okay, no, I'm sorry. No matter what happens, since this is electron rich, this Fermi level will more or less not move. Like, the more potential I apply, the more electrons it is going to pump through the oxide layer into my semiconductor. So what happens is the semiconductor is initially p-type, and it is a hole rich region. Now as Vg increases, more and more electrons are moving from the metallic electrode into the semiconductor. Now, what does this imply for the semiconductor? This means that the electron concentration is increasing over here and the whole concentration is kind of coming down. So how do we see that happen? So that phenomena we usually observe by, not observe, we represent it as band bending. So if I have this interface over here, so what happens is, as the voltage increases, the conduction and valence band start bending near the oxide semiconductor interface. So this bending is caused by the influx of electrons from the metallic electrodes. So, and this condition, this situation is what we call the depletion regime. Although it's, I mean, we need not call it the regime per se, but nonetheless, this is the depletion regime. So now in this, we would like to study the following. We want to find out the approximate electric field, the depletion charge, and the depletion width. So the depletion width, for purposes of understanding, is this. So this is WD. And yeah, just to reiterate, this derivation was also done in the lectures. I'm therefore going to just move very quickly. I'm not going to solve this using the Poisson equation. I'm going to use certain approximations. If you want the detailed derivation for this, go to the last lecture of week 10. So that is where you shall find this. However, what I'm going to do is simply use some intuitive guesses to kind of say what the electric field and the other things are going to be. So first thing we need to understand is this depletion charge QD is not a mobile charge. This is a static charge. So why is this a static charge? This region is initially hole rich, which implies there were like electron deficient atoms present over here. So as more and more electrons start coming in, those extra electrons kind of occupy the vacant sites that were created by the acceptor atoms. So now the acceptor atoms gain a negative charge, and because of that, these are, I mean, since they are atoms, they are not mobile for the purposes of conduction, which is why they are static charges. Okay, so this is the depletion width. So the region up until which the band bending effect is pronounced. And yeah, so let me insert a new slide. Yeah, so first thing we shall do is we know that at any given point, like the electric field is given by this. Yeah, so this comes from Gauss law. So essentially, we have like integral E dot ds is q by epsilon, and since this is a plane surface that we are considering, this kind of, we can do the Gaussian pillbox over here. There is no charge present on this side. There is a small charge present over here. So from that, we will get E is equal to this. And since, as I said before, the charges will be a negative static charge, this will be a negative value. So this signifies a decreasing this gives us a negative electric field, so this will also indicate the direction in which the electrons will move. Okay, so now we know that at the interface, I know that the acceptor concentration is Na, therefore if a single electron were to occupy each acceptor, this implies that the total charge at the interface is definitely going to be minus q times Na, and we need the charge per unit area. So yes, I should have. This is not q by epsilon. I'm sorry. It should have been sigma by epsilon. where sigma is the surface charge density. Apologies for that mistake. And Na is per unit volume. Therefore, Na divided by the depletion width, that is going to be sigma. Sorry, Na multiplied by the depletion width is going to be sigma. So we have E is equal to minus Q Na times Wd divided by epsilon S. So this is the semiconductor's permittivity. So this is the first expression that we have. This gives us the electric field at the interface. So now what we shall, another thing is, as we move farther and farther away from the depletion region, the material, reverts to its natural behavior. So at y equal to, so this is E at y equal to 0. So at y equal to Wd, I can assume that, I can validly assume that, oh, not D, it is Wd is equal to 0. So what I'm going to do is, for as a first order approximation, I'm going to take a linearly varying electric field. So it was originally this much, and then comes down to this. Yeah. So over here, like what I'm doing is I'm writing the magnitude of the electric field. So this is QNA WD epsilon S, and this is 0, and this is the y-axis. Here it is 0. I should have put the 0 there because it's a different axis. And this is WD. So this is the case. Yeah. So this is the variation of the electric field, and so this gives us the approximate electric field at the uh, interface. Now, how do we find the wait, the question? Okay, so I should have also mentioned mean electric field over here. So a small rectification. This is not just the approximate electric field. This is the mean electric field in the system. So now how do we find the mean electric field? So since this is varying linearly, I can directly get the equation E of y is equal to Q times Na. Like again, I'm only worrying about the magnitude here, divided by epsilon E. So at y equal to 0, it is that, and I'm assuming it is varying linearly. So what I'm going to do is I'm just going to write this by epsilon s times y minus Wd. Yeah, so this also accounts for the sign. So although, yeah, you don't need the minus sign here, assuming q itself is negative. Yeah. So in that case, this is going to be Wd minus y. So that in that way, I'll like have the same expression that are present in the lecture slides. So this is the expression. So from this we can also get the electric field, which is that just the derivative of this. So from that we will get it is Qna by epsilon s. Uh, so now this is the electric field at any point over here. So to get the average electric field, E average, what we do is we integrate from 0 to Wd. Like we can integrate from 0 to infinity, but we know after Wd it becomes 0, so that doesn't contribute, times E of y dy divided by dy. So this comes out to be Q dot Na divided by epsilon s 0 to Wd times, so this thing is Wd times y minus y squared by 2 varying from 0 to uh, so yeah, let me just write that. So this is WD into y minus y squared by 2 in the limit WD to 0 divided by WD. So from that we will get the expected answer that the average electric field is Q times NA into, so this will be WD squared by 2, the WD and WD will cancel each other out, so this is WD by 2 epsilon s. So this is the average electric field. So, and this is to be expected because I assumed it varies linearly. Since it varies linearly, the average is going to be the value at the midpoint. So that is at WD by 2. So I could have directly done that, but nonetheless I just did the integral. So yeah. So that gives us the approximate expression for the average electric field. Now we want to find the total charge that is present in this device. So yeah, so before we estimate the charge, what we shall do is we shall get the depletion width. So we know this to be the case. So we know that this is the electric field, and in addition to this, whatever Vg is applied over here. So whatever Vg is applied over here, like let me use a different color now. So whatever Vg I have on the gate electrode, after passing through the um, oxide layer, at this point, it will manifest itself as a surface potential psi s. Okay, so that psi s is kind of what dictates the variation of the electric field in the substrate. So, and again, well into the substrate, the voltage is equivalent to the substrate voltage, which is grounded. So, I have a second relation, which is integral 0 to infinity E dot dy is equal to the potential difference. Like essentially, I shouldn't write it as psi s, I will write it as psi 0 minus psi infinity. I know this quantity is 0. So, and psi 0 I'm calling psi s. So this is just the area under this curve, which is the area under this triangle. Therefore, E naught into WD divided by 2 is equal to psi s. So this is our second relation. Now we can write what the depletion width is, because now we have two equations. So this implies WD, or rather let me write E naught is equal to psi s, 2 psi s by WD, which is also equal to Q times Na into WD divided by epsilon s. So this will imply WD is equal to square root of uh, 2 epsilon s psi s divided by, yeah, Q times N. Oh, not W, N A. N A. Yes. Let me write this a bit more neatly. Looks like that thing is out of the square root. square root of yes twice epsilon s psi s. So these s's are different. Like epsilon s is, let me just clarify that over here. Epsilon s is the semiconductor permittivity, and yeah, q times Na. So now in terms of the known parameters and one unknown quantity which is psi s, which we shall come to pretty soon, uh, we kind of know what the depletion width is. For a very approximate case, we can even assume that no voltage is being dissipated across the oxide. I will come to that case later. So we can, if we want to get an approximate value of the depletion width, I can also say psi s is approximately equal to Vg. But in general, this is not valid. This is not valid. Where is this valid? I will come to that pretty soon. Like that is going to be one of the most important things we shall discuss today. So, and we can just substitute that value and kind of get an idea of how deep the depletion region goes into the substrate. Okay, so we know the width now, and from this, and yeah, we know that the electric field is varying linearly. Since the electric field is varying linearly, we can also directly tell that the doping is like, of course, I'm assuming Na is the doping throughout the substrate. So I can tell that the static charge that is formed by the electrons that are supplied by the gate electrode also kind of varies linearly. So that will give us the expression for the depletion charge. So QD can now be directly, not directly, QD can now be written in terms of these parameters over here. So how do we, yeah. So this is the width, and over this, I know that this variation here is linear. So the total charge present will again be, remember that E at any point is proportional to the surface charge density. So if I divide these into many layers, like infinitely many layers of surface, I can tell that the surface charge density is also varying linearly and coming all the way down to 0 at WD. So to find out the total charge, all I have to do is again integrate this function along this curve. So from that, I will get QD is equal to, now the sign becomes important because we are actually talking about the value of the charge. So this will come out to be 2Q Na times epsilon s times size. So that is essentially this value times Q times Na. So now why is that? Because I assume that the doping is uniform. So since the doping is uniform, all I have to do is multiply this by the charge per uh, acceptor atom. So just multiplying that will give me the value here. So QD is this. So where do I get this from? This is essentially Q times Na, or rather minus Q times Na into W2. So this is again, this charge is per unit area. So this is per unit area. So this is not the total charge. So that way, I just multiply this with the charge density and WD. WD I found out to be this. So when I multiply this, we'll get this to be our depletion region charge. Again, this is an immobile charge. Okay. So Now this gives us an idea of some things. So first and foremost, the thing that we know is QD is proportional to psi s to the power half. So the charge that is being accumulated, I shouldn't say accumulated, the charge that is being formed. Yeah, I will not use the word accumulated because accumulation refers to a different mode of operation for this device. So the charge that is being, introduced into this substrate, at least in the depletion regime, varies as the square root of the surface potential. And up to a certain limit, I can say this is approximately Vg. Therefore, in the depletion regime, the charge in my substrate increases as proportional to the square root of the applied voltage. Okay, it is not exactly square root of the applied voltage, it's the applied voltage minus something. We shall look at that in a few minutes. So this is the important takeaway from this particular exercise of ours. So over here, let us say that I am assuming, so yeah, before I move on to the next problem, let me just take a small numerical example to kind of get an idea of what these quantities are. So let me say Na is say 10 to the power 16 acceptor atoms per cubic centimeter. So we have this. And let me say psi s is, let me say it's 2 volts for now. Although 2 volts is too high. Yeah. Because let me say psi s is 0.5 volts. Yeah, that is more appropriate. And we know epsilon s is 10.8 epsilon naught. So this is the dielectric constant of silicon. So we are considering doped silicon over here. So SI dielectric constant. Wait, is it 10.8 or just 1 second? Let me look this up. I think I made a small mistake. So just 1 more second. Yeah, apologies for that interruption there. There was a minor network issue. Yes. So yeah, this is 11.8. I'm sorry, this was 10.8. So we have this, and what else do we need? Yeah, we need nothing more. So in this case, first let us try to estimate what the depletion width is. So WD, as seen before, was 2 into epsilon s into uh, psi s divided by q times Na. So this will come out to be 2 into 11.7 into the permittivity of free space. So that is going to be into 0.5. So this is going to be 0.7 into 7 naught into 0.5 divided by Q into. Now here, what should be remembered is, since I'm taking all these units in the SI form, this per cubic centimeter should also become per cubic meter. So that will give me a factor of 10 to the power 6. So over here, this will come out to be 10 to the power 22. Please don't take it as 10 to the power 16. So always pay attention to the volume unit here and the units in which you are using your different constants. So if the constants are given in SI units, remember to switch this to meter cube. If the constants are given in CGS units, then distances are measured in centimeter. You can go ahead and use the same values. Okay. So this is 0.5. So this will come out to be approximately 2.5 into 10 to the power minus 7 meters, which is 250 nanometers approximately. So as you can see here, this is actually, like, that's why I didn't want to take a larger voltage, because had I taken a larger voltage, this depletion width would have been like enormously large. So what you can see here is, if I take Na is equal to 10 to the power 16, then uh, I have a depletion region that is actually pretty deep. Like, it is 250 nanometers, and in our course so far, we are looking at devices with channel length of at most, a few tens, like 10, 20 nanometers, or even less than that. So compared to that, this is very large. So this immediately tells us that, these numbers kind of correspond to a bulk device. These do not correspond to a, so this automatically signifies that we are dealing with a bulk device, like the parameters that we chose here. Now we can immediately ask ourselves a question: what are the things that we can actually change here? Like, ideally, I would want the voltage to be, controlling voltage to be something, somewhat larger, because I don't want it to be very small, because in that case it will become susceptible to noise. Because if I'm using a very small controlling voltage, then it will, even noise fluctuation can trigger my device, which I do not want to happen. So my controlling voltage needs to be somewhat large. It cannot be very small. So the only thing that I can pretty much change, and this is a universal constant, or rather a material constant. So the only thing that I can change are either the material that I'm taking into consideration, or I can change the doping concentration. So this will become an important factor in our like subsequent topic of discussion. So this is how we find the depletion width, and similarly we can get the other quantities also evaluated. So now that I found the depletion width, I can also find the average electric field, and from that we can get the we can go on from that. So here I just wanted to show that the numbers that we typically consider are of course for bulk devices. Okay, so moving on to the next question now. Using the previously obtained results, calculate the inversion potential and the inversion thickness of the MOSFET. So now what we have to do is, we'll have to come and discuss about, we have to go ahead and discuss the notion of inversion. So for that, what I'm going to do is, I'm just going to see if I can do this. Yes, I can definitely do this. So I'm just going to copy this figure from here and paste it over here. This all the way. Yes. Yeah. So that will save me a lot of time. So now, what do we mean by inversion? So inversion is essentially whatever. So remember that in an NMOSFET, yeah, I should have also lifted that. So in an NMOSFET, my source and drain are N-type, N-doped materials. So since they're end-doped materials, I would expect that my channel will be conducting if and only if, not if and only if, conduction will be free if the channel also has the same doping behavior as the source and drain electrodes. So I would want a particular region in my device to now behave as a p-type, an n-type material. Like initially the bulk is a p-type, the substrate is a p-type material. Now I want it to behave as an n-type material. So how do we achieve that? We achieve that by increasing Vg further and further and further, such that, like, going back to this figure, whatever difference I have over here, like essentially this difference, let me call this, uh, or rather than that, that is the wrong thing. So let me call this psi b. Now, when my device has undergone inversion, whatever height I have above here, let me say over here, so this is the difference between the Fermi level and the uh, conduction band. Initially, through the process of bending, I would like to go to the exact opposite of that, which is why I refer to this as inversion. Okay, so whatever this is, so that is going to be more or less over here. So I'm going to say yes. So I want this much of a bending, and therefore correspondingly the valence band would have also bended by a like commensurate amount. So that would also go all the way down here. So now, very close to the interface, the Fermi level is like well above the conduction band, which implies this region will now become, this region becomes, or rather, shape it this way, this region becomes electron rich. So this is what I refer to as inversion. So this is, if I call this psi b, then what I want is the surface potential here should take care of this psi b and supply another psi b over here. So now psi inversion, like rather than the depletion case, the inversion surface potential, psi inversion, is equal to twice psi b. Okay, so this is what we require for the uh, inversion to be achieved. How do we go about finding this value? So that is actually not too difficult if we are dealing with bulk devices. So this is another reason why we are dealing with bulk devices, because defining psi b again for nanoscale devices becomes a non-trivial matter. Like we will have to go into other properties of the devices and use other methods, some of which are not very straightforward to do this. So first and foremost, I need to find out what the inversion potential is. So to find that, what I want is, so yeah, since this material is p doped, the whole concentration, the whole concentration for this, the whole concentration is approximately equal to Na, and the electron concentration is Ni squared by Na. So this we know from our basic, semiconductor devices theory. Now, in the presence of a voltage, N is Ni squared by Na into e to the power, like it's going to be q minus minus E by minus delta E by kBT, but delta E here is the negative charge multiplied with the voltage, a positive voltage. So the negative and negative charges cancel out. So I'm going to get psi S divided by kBT. So this is what I get. Now what we want is an inversion, which implies as many holes as we had, like essentially as many holes as I have here, I will want those many electrons to be present in my device when inversion is achieved, at least very close to the uh, interface, the oxide semiconductor interface. So n at 0 is equal to ni squared by na into exponential q times psi inverse divided by kBT. So this should be equal to Na. Oh no, I'm sorry. Just one second. Yeah, apologies. There was another minor network issue. So I shouldn't have called this inversion yet. So what we want is, so when I apply exactly psi b, this thing will come down to 0. So yeah, which implies an equal number of electrons have been introduced. Therefore, at that point, the charge at the surface is going to be 0 because there were also Na holes. So if there were Na holes and Na electrons, the total charge in that region is going to become 0. Okay, so for that case, so that is the neutralization case. So for the neutralization case, we will get psi b is equal to, so essentially just move this here and take the logarithm of that. So we will get that to be, what will it, so that is going to be kBT divided by Q, or rather it is going to be 2 times kBT divided by 2. Oh no, oh yes, this is psi b by, yes, 2 kBT because Ni squared has the variation of e to the power. Yeah, so this is going to be this. Sorry about that. So yeah, this is going to be into natural log of Na divided by Ni. And for full inversion, I will want psi inversion is 2 times psi b. So this gives me what psi b is. Therefore, psi inversion is 2 times this. So 2 kBTQ by Na by Ni. So to find, and typically you can assume Ni to be 10 to the power 10 per cubic centimeter. So this is a good enough approximation. And Na, of course, depends on the doping concentration. So again, before we move further, I mean, yeah, we don't have to move any further. Like, so this is 2 times this. Just one second. Yeah. So psi inversion is equal to 2 times psi b, which is equal to 2 kBT by q into log or natural log Na by Ni. Oh no, small n Ni. Okay, so Ni we are taking as 10 to the power 10. So again, let us assume Na is equal to 10 to the power 16 per cubic centimeter, and let me say T is equal to 300 Kelvin. So for 300 Kelvin, we know the following. We know that kBT by Q is 26. Sorry, is 0.027. So this is going to be 27 millivolts. So this is no. So now we want to find out what the inversion voltage is going to be. So that is going to be 2 into 27 into natural log of. Now here what we can say readily is that since both are given in the same units, I don't have to do any conversions. So this is going to be 10 to the power 16 divided by 10 to the power 10. So this is 2 into 27 into log 10, or rather, so by using the base change rule of logarithms, this is going to be 6 into natural log of 10. So no, natural log of 10 is going to be, or rather it will be log e to the base 10. So this is inverse of this. One divided by natural log of 10. So that is, oh no, if I multiply and divide that, it is multiplied. I'm sorry. Because log to the base 10 is always going to be smaller than log to the base e. So yes, natural log of 10. So natural log of 10 comes out to be 2.3. So there is another 2.3 over here. So this answer comes out to be 27, that's 54, 6 into 3. Yes. So now this comes out to be approximately, sorry, 745 millivolts, which is 0.75 volts. So this is the surface potential that is required to achieve inversion. So now again we can go back and see that this value that I gave here for psi s is equal to 0.5 was a valid choice, because inversion would not have been achieved at this voltage. We would have still been in the depletion regime. So for full inversion, I will need 0.75 volts. And this is, very close to the value that the threshold voltage that we consider. So, which is, that we've considered in our previous numericals. We always assume that VT, like it was assumed, sorry, assumed that VT is equal to, 0.7 volts in our previous week's problems. So now you can see that that value also is kind of in the right, ballpark. So now through this explicit evaluation, we have seen that it comes out to be, approximately 0.75. So therefore, the choices that we have made so far for threshold voltages and all of these things are kind of where they are supposed to be. So now that we have found that out, how do we go about finding the inversion region thickness? So to find the inversion region thickness, again we are going to adopt a similar strategy. So what we shall do is to look at the inversion layer thickness, we shall simply How do I do this? Yes. So to get the inversion layer thickness, now what we shall do is we shall first try to estimate the total charge in this region, and then again assuming the uniform doping uh, approximation or assumption, what we will say is the inversion thickness multiplied by that uh, sorry inversion thickness divide sorry the doping concentration multiplied by the inversion thickness will give us the total charge that is stored here. I'm sorry, I got a bit confused with my words there. So what I will essentially say is Q inversion is equal to minus Q times Na into T inversion. Or rather than saying Na, what I will say is minus Q times small n, yes, of 0 into T inversion. This will give me the total charge. Now I know this quantity here can again be written as uh, yeah, minus Q. So this is equal to minus Q into Ni squared yes, Ni squared by Na just 1 second. Yeah. So this is N0. So this is going to be e to the power Q times psi. Now we know that this is the inversion charge over here. So I will just write this as, or you know what? Let me say that I'm increasing the voltage beyond the inversion point. So then I can just replace this by the surface potential once again divided by kBT. Now this is the charge over here. Now how do I get the uh, average length? So for that I will just once again, I mean it's not an effective, it's not a correct approximation, but once again I will assume that the electric field is dropping linearly through this system. So if I assume that, going back over here, where did I derive that? What was the average electric field derivation? Yeah, that's over here. So going back over here, I know that the average electric field has been derived to be this quantity. And this is related to the width of the region by this expression. So now this quantity will be replaced by the new inversion charge that we have obtained. So by just substituting the values, I will get a factor of kBT divided by Q into, okay, I shouldn't write an epsilon here because we've been using epsilon for that, E average. So this gives us the inversion layer thickness. Now inversion layer thickness, yes. So ultimately it all depends on the average value of the electric field. Yes. So this is T inversion. And this quantity here is the value of Qn0. Okay, so the takeaway over here is that Q of psi s is proportional to e to the power size, e to the power k times size, or to be more precise, log or natural log of Qn of psi s is proportional to size. So this is the important takeaway from the inversion region behavior. So now we have seen the inversion behavior, we have seen the like depletion behavior, we've also done a sample numerical in both cases. So this is the inversion layer thickness, and everything boils down to how the electric field varies in the substrate of my device. So if the electric field varies more or less uniformly, then we will have a different kind of behavior. If the electric field falls off rather quickly, then we will have a different kind of behavior. So that is what we are going to see in the effects of electrostatics. So before I begin with the third problem, let me quickly give you an overview of the form factor. Because if I go into the, not form factor, the body coefficient. So, yes, if I go into the derivation of the body coefficient, I will end up taking another R, which is not feasible. So, what we can understand, like right away, is when I'm applying a VG, now this device can be modeled as follows. So I know that there is an oxide, which of course acts as a capacitor. So this is a dielectric. I have a metallic electrode on the one side, and when inversion is achieved, I can assume that the other side of it also has, somewhat metallic-like behavior, because metal-like behavior, because it is electron rich. So that brings me to the interface point. So this corresponds to the y equal to 0 point. So I have the oxide capacitance over here. And what we should remember is, even past the complete inversion region, there is a depletion region here. So there is a depletion capacitance that also forms simply because of the way in which we are operating the device. And this is ultimately, like in our current model, this is connected to Vs equal to 0. So now my device has two capacitances. Therefore, the total capacitance for two capacitances in series is going to be, so C total, or let me call it the gate capacitance, C gate, is going to be CD. So that is going to be, yeah, just one second. So that is going to be 1 by Cg. Why do I keep writing G before C? Cg is equal to 1 by oxide capacitance plus 1 by Cd. So this gives us Cg is equal to Cox into Cd divided by Cd plus Cox, and this further implies, therefore, Cg is equal to Cox. Let me take the reciprocal of this factor, so I will write this as Cox by M, where M is equal to the reciprocal of this, so that is going to be uh, 1 plus Cox. Am I writing this correctly? I'm sorry. I should have written this as CD. Yes, Cox should have been kept inside. Yes. So now this is going to be 1 divided by CD by Cox. So this is the uh, quantity that I call. So this is the quantity that I call the body coefficient. So this is the quantity that I refer to as the body coefficient. So CD divided by Cox. Yeah. Now what does the body coefficient do? So as you can see here, ideally speaking, I will want my gate voltage to directly influence the surface potential. So over here, the voltage that I have is, or rather, I shouldn't put it over here. Effectively, psi s is achieved at this point because, like, I will have to traverse through the entire depletion regime and then arrive at the inversion point. So ideally speaking, I will want my gate voltage to directly get reflected in the, yeah, so this is CD by M. So directly get reflected in my substrate. But because there is this second capacitance CD that kind of varies. So a certain voltage drop occurs. So essentially this implies that psi s is Vg minus uh, Qn divided by Cg. So this is essentially what happens. Like there is a potential drop over here, and because of that, I have a Q in the device divided by Cg. Now, as Cg becomes smaller and smaller and smaller, we will know that this voltage drop becomes larger and larger and larger, which implies I will need to apply, essentially what this tells me is, and inversion depends on this quantity here. So as Cg becomes smaller and smaller and smaller, I will need to apply a larger and larger gate voltage in order to switch my device from on to off. So that difference becomes significantly larger. Okay. So of course, there are some other effects here also, like substrate capacitances effects also, but I'm not considering them. I'm only considering the depletion capacitance. So ideally speaking, I will want CG to be as large as possible. Like technically speaking, I will want CG to be infinite. If CG is infinite, then all is well and good, and no voltage drop will occur. But that is never going to happen. So now, what is the factor that is affecting me here? The factor that is affecting us here is, if you look at this quantity here, then the relation between CD and Cox, the oxide capacitance, tells us how far from, or rather how, like, if this quantity becomes greater than 1, then Cg becomes smaller, which is something that we don't want. So this implies Cg has to be small. So this is the reason why Vg does not directly influence the gate voltage, and the surface potential is what that, not Vg doesn't directly influence the channel inversion. The surface potential is what influences the channel inversion, and I will want Cg to be small for better Vg control. And the smallest value Cg can have is, so Cg min, or min of Cg, is unfortunately equal to Cd, because anything like Cox has to be infinite. is like one way we can achieve that. Okay, so this is the smallest value it can have, and as a result of which we have uh, I'm sorry, just one second. Oh, no, 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 no. Yeah, now I understand why I was getting those things. So that is not, the body coefficient doesn't come up over there, it actually comes over here. Yes. Cg is equal to, this was my original quantity was correct. Cox into, yes, Cd by Cox plus Cd. I'm really sorry for this. Okay. Yeah. And we have, and forget about the definition of M for now. So this is the thing. Now Vg is this. So from this, what we will get is, so this quantity, so I can just write it as Q as Cv. So Cg times Vg. So psi s is going to be Vg into 1 minus, yeah, yes. So why did I write Cox here? The reason I wrote that is, ideally speaking, this is what I would want. So this is the expected behavior. Like I will want all, like whatever voltage drop I want, I will want it to happen across the oxide layer, and no voltage dissipation should occur, like gate voltage dissipation should occur in the substrate. So I will want a situation like this. However, I know Cox is like Qn actually depends on more than the oxide capacitance. So this is my expected behavior. Because I know Cox because I fabricate the device. So that way I will know what the relation between Vg and the surface potential is. But however, due to depletion effects, that no longer remains the case. And also Qn is equal to Vg times Cg. Yes. So, now it's not Vg minus, I'm sorry, it is Vg into. So now this will give me 1 minus Cd divided by Cox plus Cd. So this is going to be, sorry, Vg into, so this is going to be Vg times Cox by Cox plus Cd, and this is equal to Vg by M, where M is equal to 1 plus Cd by Cox. Yes. So ideally speaking, I will want my device capacitance to be only the oxide capacitance. I will want CD to be infinite, but that is never going to happen, because for CD to be infinite, uh, I will either, okay. So that is, let me say that is, let me not say that is never going to happen. So let me simply say here, ideally CD should be very large. CD should tend to infinity. Then I will have this kind of a situation here, and that will kind of reflect in our uh, like device behavior. Okay, and this quantity M is the body coefficient. Sorry, yeah, it is a body coefficient. Okay, so this is the body coefficient. Now we have two questions here. Initially, we are told that the body coefficient is 5 by 3. Now, first question that is asked is what will happen if the value of the what will happen to the value of the body coefficient if the oxide capacitance is doubled. So yeah, if the oxide coefficient is sorry oxide did I just say oxide coefficient? Oxide capacitance, yes, oxide capacitance is doubled. So how do I double the oxide capacitance? I can do that by either increasing the area, but we don't want that because that will also effectively increase the channel length. I can make the oxide layer thinner, or I can say epsilon s becomes 2 epsilon s. I can double the dielectric constant. So if we do that, then I know Cox goes to 2 Cox. Now I know M is equal to 1 plus CD by Cox is equal to 5 by 3, which implies CD by Cox is equal to 2 by 3. Now if this thing becomes double what it is, then from 2 by 3 it will become, so if Cox becomes twice Cox, so this is question A, 2 times Cox, then this ratio, what shall we call it? I mean, it is m minus 1 technically. So m dash minus 1 is equal to 2 divided by 2 into 3, which is 1 by 3. Therefore, the new body coefficient is 1 plus 1 by 3, which is equal to 4 by 3. So ideally, I will want CD to be very large. Where is CD to be very large? Yes, I did write that. Was I right in writing that? So this is going to be Cox. Just 1 second. I'm sorry for this confusion. Uh, just 1 second. I'm once again very sorry. CD shouldn't be very large. Again, in the flow I just uttered that CD should be very small. The body coefficient should be 1. M should tend to 1. Okay. That is when psi s will be Vg. Will be Vg. Okay. Will be equal to Vg. So, sincere apologies for that confusion. So yeah, CD should be very small, because if CD is very small here, then that will imply the total, gate capacitance becomes 0. Since gate capacitance becomes 0, that implies there is very little charge accumulation. All the like voltage will contribute directly to inversion. There will be no charge depletion. There will be no unnecessary static charge accumulation in my system. So when this capacitance, gate capacitance becomes infinite, then or rather when it becomes as small as possible, it won't become infinite, because when oh no, it will become infinite. Sorry, it will become 0. When the reciprocal of it becomes infinite, then Cg will become 0, which implies Vg times Cg will always be 0. So the static charges in my system will not be present at all. Therefore, any charge that comes into my device directly becomes forms the inversion layer, and my device is ready to function. So I will just have a small minor threshold voltage that I will have to clear, and once the threshold voltage is cleared, and the threshold voltage of course will can be determined directly from the doping concentration. So that will tell me where the quasi-Fermi level is. I know the band gap of the material. So from the difference of the two, I can directly determine what gate voltage I need to apply to achieve inversion. But because of these CD that is present here, some of the charge, like some of my applied potential will first have to help us overcome this depletion regime. Okay. So, yeah. So now, so the bottom line for everything that I told is previously M was 5 by 3, now M has come down to 4 by 3. So this is closer to ideality. Okay, now case B. B is, we are saying Na prime is equal to Na by 2. So the acceptor doping is halved. Okay, so this happens. Now, what impact will this have on the device? So the impact that it is going to have is actually quite straightforward. The impact that it is going to have is CD will change. Now, how do I find CD? Worry not, we already know what CD is from our first problem. Now remember, we know that this is the width of my capacitor. This is the width. Okay, so where are we? Yes, so CD is simply epsilon s divided by WD. That's all. Like there is a factor of A, but I don't worry about it because I'm writing capacitance per unit area. Okay, so in this case it is simply going to be epsilon s divided by square root of 2. Let me just go back to be doubly sure. Yes, epsilon is psi s by q times Na. Psi s divided by q times Na. Okay, so now what we have been asked is, sorry, I should have undone that. Yes. So this is a depletion capacitance. So the question that has been asked is what will happen if Na goes to Na by 2? If Na goes to Na by 2, then CD goes to CD by root 2. That can be seen directly over here because the factor of 2 over here will go to the numerator. So that will be 1 by root 2 times this entire quantity. So this implies, now again, previously we know CD by Cox is equal to 2 by 3. Now halving the acceptor concentration or the dopant concentration in general, this will become, so now this is essentially, this means that how do I write this? Yes, CD is 2 by 3 times Cox. Now CD has become CD by root 2. So that is 1 by root 2 times this quantity. So this ratio will become CD dash by Cox. So over here, M minus 1, this is equal to CD does not change here, Cox changes. So Cox dash, here CD changes. This is 1 by root 2 into 2 divided by 3. This is equal to square root of 2 divided by 3. This comes out to be yeah, 0.47. 0.47. Okay. So this implies M is, I mean, I could have also written it as 3 plus root 2 by 3, but you know, that doesn't look so nice. So this is approximately 1.47. So in this case, this is 1.33. So through this problem, what we have seen is we have seen two ways to reduce the form factor. Essentially, bring our device closer to the ideal behavior case, where depletion no longer saps the extra potential away from the system. So now, before moving on to the next point, why are we doing all of this? So what we want is, let me say, I'm considering this. So yeah, let this be psi s, and let this be uh, yeah, let this just be q now, or rather mod q. Now the point is, for an n MOSFET, we know that in the depletion region, initially this increases as square root of psi s, and then after inversion is achieved, this kind of moves up to an infinite eventually, directly run up to infinity, kind of becomes, yes, like this. So this is how we see the variation. Yes. So this is the depletion region, regime, not region. This is the depletion region, regime. Apologies once again. So depletion regime, and over here we have achieved inversion. So beyond this we have inversion. So I have psi s to the power half. I have e to the power psi. So this is a region. This is the cost we have to pay to reach here. Remember, I didn't say charge was being accumulated previously because I said that's a separate regime of the device. So that is over here. Essentially, when I apply a negative voltage, what I will do is I will start drawing more and more electrons from the semiconductor towards the metal. So when I do that, the whole concentration will start rising further and further and further. So there is no barrier that needs to be crossed. So quite immediately it will, quite immediately it will start showing the exponential behavior. Okay, yeah, this shouldn't have been away from zero. Technically, yes, it won't converge directly at zero, but you know what? I think I will make it converge at zero because, yeah. So this is how the variation happens. So here it is again proportional to e to the power. So here, this is e to the power size, like, constant time size. It's not just exponential of size. So for negative, so this is the accumulation regime. So this is the accumulation regime. So here I have holes, and over here I have electrons. So these are the conducting like majority carriers. These are the majority carriers over here. So ideally speaking, I will want this to become smaller and smaller and smaller. So when n is equal to 1, this will become the smallest. Like essentially this will just be a small bump over here and it will just rise. Ideally, however, so this is in a conventional MOSFET. Ideally, what kind of a behavior I would want to see is, or one would want to see, we would want to see is something like this. Like now, what I'm writing here is natural log of q, natural log of mod q, to be like very correct, because log of negative is not, like, it's not a real number. So in this case, what I would like to see is after a inversion threshold, This will just rise linearly. Like ideally, I would want something like this. So this will start rising linearly with psi s, and similarly, after a certain threshold, the device will start rising linearly. So in this region it is off, and in this region the device is on with the variation of size. Ideally speaking, I will want something like this. Now here you can see that this part is kind of achieved already, but here before achieving this linear trend, there will be a small, fluctuation here. If I draw this in this curve, that's why I do this in like the normal units over here. Okay, so this is the preferred behavior. So this is what is preferred. Oops. So this is the preferred behavior. But what we have is, so this is what we observe. So our whole aim can be summed up in this quantity, the body coefficient. If I can bring down the body coefficient to as small as possible, then I can mitigate most of the electrostatic effects. Now, what are the electrostatic effects? We shall look at it in another way in a moment. So, so the aim is to reduce body coefficient to 1. So that is the aim here. Now, how do we, so one way to do that, like two ways we have already seen. A, use high dielectric oxides or insulators. And the second is use lightly doped semiconductors. Okay, but both of these come with their own respective drawbacks. The first drawback here, this would imply we will need to use new materials. Therefore, our corresponding fabrication techniques and the material, the ways in which we obtain the material and process them, they will all change at a fundamental level. So, like you might have seen, like in the lecture, high dielectric materials are things like so these are what, like hafnium dioxide or you know zirconium dioxide or things like that. So we'll have to go into like rare earth elements. Okay, so rare earth elements will kind of give us this, but again, those are rare earth elements and they are expensive, which implies device manufacturing costs will go up and fabrication methods will also need to be changed correspondingly. The drawback with using lightly doped semiconductors, although this seems to be a good, and there is also a third method that I kind of discussed offhand. Remember, I said this, or Tox tends to Tox by 2 implies Cox tends to Cox by 2. So this is also possible. Now again, reducing gate thickness would mean changing the fabrication methods, techniques, appropriately. Like we will need greater sensitivity to deposit thinner gates. And so we can also use thinner gates. So this will also imply like we have the same drawback as here. Now, with lightly doped semiconductors, what will happen is, remember here, when we were discussing inversion, this psi B determined our inversion voltage. Now, if the material is lightly doped, then this EF is going to go higher and higher and higher because, like, okay, it won't go higher and higher. Like, essentially, oh no, yes, we can say that. Like, if the material becomes lightly doped, then this will become closer and closer to the intrinsic Fermi level. And because of that, the inversion potential that is required will also come down, which implies now my device will be able to switch between on and off rather easily. Therefore, the sensitivity of my device becomes very high, which I don't want. Like I want my device to have a very well-defined on state and an off state, which only I can deterministically change. So this, although body coefficient comes down, we will have poor controllability for the device. So poor controllability over here. So thinner gates again needs better fabrication techniques. And let me just write these in red. So here this implies we have poor controllability. And here this means we need like better fabrication techniques. So this kind of tells us on a more practical front what we need to do to get better transistors. So either we start making our devices by incorporating newer materials, or we need lightly doped semi, we change the doping levels of our semiconductors, or we use thinner gates. All of these will change how the devices are being fabricated. So that is a given. Now the point is, given that we are changing the ways in which we are fabricating the device, is there something more that we can do? The answer is yes. So the first and foremost thing that can be done is we can have double or multi-gate devices. So these are these are devices that are double gate, extremely thin silicon on insulator transistors, or even FinFETs. So FinFETs are multi-gate devices because we have a fin structure around. Like essentially, we will have our channel. How do I? So we will have a channel that is kind of going like this, and we will have a gate that kind of envelopes this. So like the gate is grown like a fin around this structure. So, yeah. So the gate will be something like this. Yeah. So it will kind of cover this. Yes. So the gate is going to be something like this, covering this entire channel. So yeah, you can kind of guess how this. Yeah, I did too much shading. Not to worry, I will make it better in just 1 second. So, oops, made it worse. Yes. So if we have this, then yeah, I can draw it with this. So yes, this is how this is going to look like. Yeah. So now the gate is a fin around our channel. So this, yes, so this is the fin structure. So this is what we call, it essentially writes the thing like a fin. So now what does, and we can also have short channel devices. Short channel devices is what we have been discussing all along. So short channel devices are essentially ballistic MOSFETs, MOSFETs and other devices. So now how do these things reduce our electrostatic effect? So I actually skipped one step here. So the thing is, if you remember, we were talking about things like essentially we are looking at 2D electrostatics. So let me go back to this figure here. Yeah, I should have mentioned that. Now, when we are applying a drain source voltage, when VDS is applied, we know things like DIBL occur. Now, why does DIBL occur? Essentially, what happens is this voltage here will also influence the charge that is accumulated over here. So, as this voltage keeps increasing higher and higher and higher, we have seen that for the classical device, a kind of a channel pinch off happens. And in the case of our ballistic devices, we know velocity saturation occurs. So, our aim now is to ensure like better gate performance, one or more of these techniques should be adopted. Like we need lightly doped devices, or we will need high dielectric insulators, or we will need thinner gates, you know, for having better gate performance. Now, when we are talking about mitigation, here we are talking about 2D effects. So what are 2D effects? 2D effects are effects that take place along both the x and y direction of this figure. So here I should point out that this is the x direction. Okay. So now our aim is to get rid of things like DIBL. So DIBL is eliminated by having a shorter channel. Now if the channel is very short, then what will happen is the electric field that is applied. So 2D effects vis-a-vis DIBM and other related effects. Like primarily we shall be concerned only with train-induced barrier lowering here because that is the one thing that we have discussed. Okay. So now what happens is if I use a short channel, like if I have a shorter channel, then the electric field that, so typically when I have, yeah, I think. So if I have a channel and I have Vg from up here and Vd from over here, then what will happen is the electric field will look something like this. So electric field lines always move from one electrode to the other. So given that all the other electrodes are grounded, the electric field lines will move like this. So they will go like this, they will come like this. And now these lines over here will affect the impact of the gate voltage. So ideally speaking, I will want my electric field lines. So this is not preferred. But if we have a long enough channel, this is always going to happen. Like there is no way to stop this. Bad English. Yeah. this is not preferred. Ideally speaking, what I would want is, I would want something like some scenario like this where the electric field just drives. Like think of it, electrons moving will now no longer go from source to drain. They will move from either source to substrate or source to gate, which implies the current conduction is no longer going to take place properly. That is all is implied by these, bending electric field lines. This is what I would ideally prefer. So I have my drain, or rather source here and drain here. I shouldn't say drain and source. Technically speaking, yes, it will be drain and source because we are talking about electrons, but it doesn't matter. So yeah, ideally speaking, I will want something like this. I will want the electric field to drive my electrons from source to drain. So in that case, the arrows will be the other way around. Don't bother about it. Like assume this is a PMOS and not an NMOS. So I have my gate voltage over here. Now, there are two ways of achieving this. Method one, surround this device by gate electrodes so that the gate electrodes, gate voltage kind of straightens these lines out. Okay, so that is what is achieved in devices like FinFET, where by surrounding it or by using double gates, I kind of reduce this bending effect. Second method is geometric screening. What is geometric screening? I just reduce the geometry of the device. So since the geometry of the device is reduced, even before these lines can start bending, they will encounter the drain. So when I have a shorter device, yeah, okay, I should have said shorter device. When I have a shorter channel, I have what is called geometric screening. So in this case, it is literal electrostatic screening. Like I just surround it by electrodes and apply voltage. So I'm electrostatically screening this channel from the adverse effects. So that is the first two methods. So these employ screening. Now the second methods, so these two here, so quantum confinement we can do by having say nanowire transistors or quantum dot devices. So quantum dot devices, even single electron transistors, these are all under this category. So here what we do is we kind of do away with the conduction problem altogether. So now like the whole process kind of becomes quantum mechanical. In the nanowire case, we have already seen how the modes and other things are formed. So there again, none of these behaviors can be observed anymore. And the final method is what is called strain engineering. Now again, to, of course, double gate and short channel devices, these are kind of a thing now. So by short channel, what I mean is this should be like 6 nanometers or lesser than that. So this comes from the de Broglie wavelength of the thermal de Broglie wavelength of an electron. So we know that, I mean, people who are aware with the industry trends would know that a long time, I mean, for a very long time, we have been operating below 10 nanometers. So FinFET, I think the standard these days is 7 or 5 nanometers. So we are very much in this range. So this approach has already been standardized. So this is very much in presence. This is such devices are present in the devices that we use in the present day. These devices, of course, are an active area of research, and this is kind of what we have been pushing towards. Like quantum confinement and strain engineering is also done through quantum confinement. More on this will be discussed next week. So I'm just going to give a brief introduction to these two. Now, strain engineering can also be done using EDSOI devices. So EDSOI is not only like multi-gate devices. They are not only multi-gate devices. We can also have strain effects over there. And here, what we essentially do is we just increase the mobility of the electrons. Since the mobility of the electrons is increased, even if a small source voltage is applied, electrons will just rapidly rush towards the drain. Like they will not worry about any other voltages. So we will make the drain source voltage the determining factor of the current. So in that scenario, what we do is we kind of make the electrons so mobile that, or rather make the electrostatic effects so irrelevant that they no longer affect us. Okay, so to finish today's session, we shall look at two numericals, one for the screening effects and the other for the uh, quantum confinement effects. So now, yes, here we are. So given that a channel has a doping length of, doping concentration of 10 to the power 15 per cubic centimeter, find the minimum channel length for achieving geometric screening. So for this, we will need to know the concept of the Debye length. Now Debye length, it has been defined in the slide, so I'm just directly taking the expression from that. So this will come out to be, the expression is this, by q squared Na, like I'm assuming P dot, and also like whenever T is not mentioned, go ahead and assume T to be 300 Kelvin. So very close to room temperature. So in this case, what we will get is, so this is going to be square root of 11.8 into kb T. So now kBT by Q, yes, I can use my previous approximation. So 11.8 into epsilon naught into 1 kBT by Q will give me 27 into 10 to the power 3, 10 to the power minus 3 divided by Q into 10 to the power. Remember, everything here is in SI units, so this will become 10 to the power 21. Okay, so I am writing it in per meter cube. So let me quickly calculate this. Yes. So now this will come out to be LD will come out to be 1.33 into 10 to the power minus 7 meters. Now the minimum channel length, lambda min, as I showed here, should be LD by 3. Okay, so the Debye length divided by 3, that is the tolerance limit we have for, like, not the, that's the prescribed length for preventing geometric screening. So, sorry, for having geometric screening. So I shouldn't have said that. I'm really sorry about that. So that will come out to be 1.33 divided by 3. So that is 4 by 9. So that's approximately 0.4. Yeah, 0.45. So that will come out to be into 10 to the power minus 7 meters, which is 45 nanometers. So for this kind of a device, we will definitely have to have a channel that is in the nanometer regime. So our target, so now through this we will see that, we can see that, mm, what was I saying? Yes, through this we can see that the current industry levels, like for channel lengths, accounts for geometric screening factors very well. So geometric screening is like utilized to the best extent, and it can also be observed that if we increase the doping, this kind of comes down. So let us say instead of 10 to the power 15, I take slightly heavily doped material of 10 to the power 18, in which case what will happen is this will become 10 to the power 24. So this whole thing will have like divided by what, square root of 1000. So that will be what? So 1 by square root of 1000 comes out to be what? That comes out to be 0.03. So in that case, this will become 1.2 nanometers. So if I use, okay, 10 to the power 18 was actually a bit high. That is, I mean, to the point of a degenerate doping. Let us say I took something like 10 to the power 17, yeah, 10 times less than that. Yes, then it will be 1/10 of this, and I would need a channel length of 4.5 nanometers, which is around our current standards. So we can even have moderately high doping, like 10 to the power 16 is good enough non-degenerate doping. So even at 10 to the power 16 donor or acceptor atoms per cubic centimeter, we can see that the present channel lengths that we have accounts for geometric screening. Okay. So the final example that we shall consider today is for quantum confinement. So here we have we are considering a bulk semiconductor undergoing biaxial, expansive or tensile strain. So I will briefly tell you what this is. This will be explained in more detail in our next week's session. So what this means, what how this is typically done is we will take a material of say a particular lattice constant. So assume that these are all equally spaced. And on top of this, we shall deposit another material with a smaller lattice constant. Okay, so let us say I'm doing this. Now, when deposition occurs, so let me call this uh, A0 and let me call, or rather let me call this AD. Let me just call this A and let me call this bigger quantity AS. This is the lattice constant of the substrate. Okay. So when this deposition is done, what will happen is a kind of lattice matching needs to take place. Only then and only then will the atoms be able to deposit on the surface. So because of the lattice matching requirement, what we will have is, again, the figure is not to scale, so kindly, you know, understand that. The bonds in the material that is being deposited. So, let me just draw the line and say, this is my substrate. So I'm going to one more layer over here just to indicate that this is the substrate. Okay, so this is the substrate. So here I'm just going to go down. So now, yes, the green dots will get stretched out. So these bonds now undergo a tensile strain. They are stretched. Now remember, if this is a 2D device, then stretching occurs. So for a 2D device, if I have a substrate that is like this, then depositing a material on this, let me just do 9 dots to make things simple. Now there will be stress along both these directions because the lattice needs to be matched along the x-axis and the y-axis. Okay, so let me say this is the x-axis and this is the y-axis, just for, then you can see that there is a biaxial stretching. So that is what I mean by biaxial strain, and there is no tensile strain for the material along the z-axis. Okay, so it undergoes biaxial tensile strain. Now estimate the new effective mass for this system. So how do we go about this? So what we should remember to solve this problem is, again, in greater detail, I shall address this in the next week's session. So what we need to remember first is that the total energy for a bulk material is h squared by 2 m star kx squared plus ky squared plus kz squared. Okay, now we can, like, so k is proportional to, like, kx is proportional to 1 over lx, ky is proportional to 1 over ly, and kz is proportional to 1 over lz. Okay, so this is the relation between k and the actual physical lengths. Okay, so this you can go back to your KP model derivations, and then you will get this, like, essentially you know that the Brillouin zone is, at plus minus pi by a, pi by l, and second Brillouin zone is over there. So I know that the k values are proportional to the inverse of the length. Now what has happened is this system has now undergone biaxial strain, which implies k prime of x is proportional to 1 over L prime of x, because now Lx and Ly for this system have changed. 1 over L prime y. So this expression no longer holds because kx and ky are changing. Now if I want to retain the same form of the expression, what do I do? What I will do is, whatever factor of change that I'm getting here, I will kind of offload it onto the effective mass. Okay, so this implies E dash is equal to h bar squared kx squared by 2. So now what I'm going to say further is, so z, let me call this z direction the longitudinal direction. Okay, so let me say z is longitudinal. Okay, so, and let me assume that Lx equal to Ly, initially Lx equal to Ly equal to Lz, just for the sake of simplicity. Okay, so therefore L, and here let me say L dash x is equal to L dash y. Hmm. So now, if I don't want to go to k dash, whatever change happened there, I'm going to introduce it over here. So I'm going to call this m dash m star x plus ky squared to m star y plus k squared by 2 m star z. Now what I will say is m star x equal to m star y equal to m star transverse, and m star z is equal to m star longitudinal. So now I have the electrons, depending on their direction of motion, have two different effective masses. Now, of course, that doesn't make much sense. Like, we will have to arrive at a single effective mass. So Overall, again, I will want an expression like this. So now I will have to replace this mass by an effective mass, and we can already see that E is proportional to 1 by n. Therefore, the effective mass, this is similar to like a serial addition of capacitors. So from this I can say 1 over m star effective. I shouldn't say effective mass, that would be wrong. So I will say m star average, yes, is equal to, now there are two transverse masses, so that is going to be 2 divided by m star t plus 1 divided by m star l. So this is the expression we have for the new effective mass. Now, if you want to ask, does the effective mass go up or come down in the presence of, say, an expansive strain, we can see that here, since L dash increases, so like I can say that L dash is greater than L because this is tensile. So in that case, the value of K comes down. Now, if I'm rescaling this, I can definitely say M star transpose is greater than the original M star. Okay, so this value will be greater. This, now you can of course do the calculation and see that since this is greater, the total effective mass will be lesser than both of these values. Okay, because it's a harmonic beam. And so the reduced effective mass of the electron implies that the mobility is now increased, because the mobility is also inversely proportional to the mass of the electron. Lesser the effective mass of the electron, the more mobile it becomes. So this is the average effective mass. So by introducing a strain into the system, I have enhanced the mobility of the system. Now, this is again a very semi-classical treatment. There is a proper quantum mechanical treatment for this as well that I shall do in the next week session. Okay, so with just this, I will, because I've done this kind of to give a solution, give a hint for an assignment question. So that is why I've done this particular question in a kind of you know loose and approximate way. I will come back to this in the beginning of next week's session, and address this particular topic in slightly more detail. So with that, I come to the end of today's session. I thank you all for listening. We shall meet again same time next week. Thank you.